So the next type of proof that I want to talk about is existence proofs. Which may be what it sounds like when you're trying to prove some kind of existential quantifier. Oops. So we want to prove that some object with some property exists. Now there are a number of ways to do this. Here are a couple examples. So the most straightforward way, and basically the best way, is just to give an example. Right? If you wanna prove that something exists, just show me, right? I'm convinced. So, for example, let's try to prove there exist rational numbers a and b such that a to the power of b is irrational. Okay, proof. Let's take a equals 2 and b equals 1/2. These are rational numbers. And if we look at what a to the b is, this is 2 to the 1/2, which is the square root of 2. And you may remember that yesterday we proved that this is irrational. Cool. Proof complete. Easy enough. Well, but not so easy always, because often coming up with an example is quite difficult. So if you give an existence proof without giving an example, this is called a non-constructive existence proof. And I gotta say, non-constructive proofs, I'm saying that they're not as good as giving an example. But I have to admit that they're quite satisfying in the sense that proving that something exists without giving an example often requires a very nice kind of cleverness. So it can be very satisfying as like a proof, even though, giving an example would be more, more concrete. Non-constructive proofs are often very pretty. So here is a silly little one. Let's do the same thing that we just did, but with a little swap. There exist irrational numbers, a and b, such that a to the b is rational. So this is exactly the same proposition, except we've exchanged the roles of rational and irrational. And this proof is going to be almost constructive, but not quite. So here's our proof. Consider the number square root of 2 to the power square root of 2. So we're going to think about a couple of cases. Case 1, it's rational. Right, so the argument we're making, the cases that we're using, are if we think about this number, it's either rational or irrational. Right? Fair enough. So in the case that it's rational, we can take a equals square root 2 and b equals square root 2. These are irrational numbers, and in this case, we are sort of assuming that a to the b is rational. So this is an example. But we don't know that this is true, so we have to consider another case, which is when root 2 to the root 2 is irrational. And in this case, we take a to be root 2 to the root 2, and b equals root 2. And what do we do here? Then a to the b equals root 2 to the root 2 to the power square root 2. And if you remember your exponent laws, this is square root 2. This is what happens, right? So if you have a power and then another power on top of it, they get multiplied. So this is root 2 squared, which is 2. And that's clearly rational. And that completes the proof, because we had two cases, and we showed that in each case, we could come up with an example. But it's still a little bit non-constructive, right? Because we have these two examples, and we know that one of them works, but we don't know which one. And I don't want to go through this in detail right now, but I just want to give a preview of a topic that I'm hoping we can talk about next week, probably, which is the following. So a real number is transcendental So this is a little.
May I ask a quick question?
Review. Yes.
So we've decided that in the first case, a to the b is rational. And in the second case, if a equals square root 2 to the square root 2, which we've decided is rational, then a to the b is taking a rational and an irrational.
So you're saying this is rational?
Isn't that what we've decided in the first case?
Well, maybe I should have been more explicit. That is exactly what we're doing with the cases. So in this case, or let me say, so case 1 is root 2 to the root 2 is rational.
Okay.
Case 2 root 2 to the root 2 is irrational. So this is just some number, but we don't know if it's rational or not. And I actually genuinely don't know if it's rational or not. Like, this is not just a trick to make this proof impressive. I think it's actually a much harder question to answer. But the fact is,
Okay.
if we consider both cases, in this case, it's rational. So we take advantage of the fact that it's rational to make this thing work. And in this case, it's irrational. So we use it where we want an irrational number. Right?
Okay. Yes. Thank you.
So this is a slightly non-constructive proof where we gave two examples and proved that one of them works, but we don't know which one. But I just want to give a little preview for there are much wilder examples like the following. So a real number is transcendental if it is not a solution to any polynomial with rational coefficients. So for example, square root 2 is irrational, but it is not transcendental because it's a solution to x squared minus 2. So transcendental numbers are even wilder. And we can prove, or let me say, claim there exists a real number which is transcendental. And genuinely, the easiest way I know to prove this is to prove that, in fact, almost all real numbers are transcendental. And therefore, one exists. But genuinely, it is easier to prove that almost all real numbers are transcendental than it is to write one down, which is quite wild and a very, striking example of a non-constructive proof.